right, go ahead.
Okay, hello everyone, welcome to our 1W-MINDS seminar. Today we are very happy to have Dr. Xie from Georgia Tech. Dr. Xie is a Coca-Cola Foundation Chair and Professor at the Industry and System Engineering School. And she's also the Associate Director of Machine Learning Centers. Her research bridges statistics, machine learning, optimizations, and developing computational efficient powerful methods with real-world applications. And today she's going to share her work on this generalized linear models, and looking forward to it. Please take away. Thank you.
Thank you. Okay, good afternoon, everyone. Thanks again, Sitting, for organizing the seminar, inviting me here. And so my great pleasure to share everyone about this work. I know it's mouthful. We purposely made it this way, generalized linear model. And basically what this talk is about is we find out there's this interesting new technique for estimating a generalized linear model and even generalize the version of that. And GLM is basically one of the most, I think, common and popular statistical models for modeling data. And so I'll explain that, and I'll explain why do we need this so-called monotone variational inequality, the new technique for estimating such models. So here's the outline. I'll start talking about motivations and talk about algorithm, theory behind it, and also applications and extensions. And this is the joint work with my collaborators, Anatoly Juditsky, Arkady Nemrovsky here at Georgia Tech, and my former PhD students, Chen Xu, and some of the work by Tina and my collaborator Xiuyan Cheng at Duke Math. And here are a list of some of the papers related, but we can talk about this later as well. Okay, so getting to the business, what is GLM? So generalized linear model is one of the most basic models in statistics. It's basically a generalization of linear model. It has some nonlinearity, but you still have some linear structure in there. So it's a particular kind of model. And so in this setting, we have observations where XTs are the predictors or the features, YT are the responses. It could be basically a scalar, that's what I mean, but it can also be, categorical or binary, such as logistic regression is a type of generalized linear models. And it's called generalized linear model. It usually means that, why these responses are related to the predictors through this kind of model. So conditioning on the predictor, the expected value of the y is going to be some link function, which is usually assumed to be no, and depending on the choice of the distribution for y, this link function is different. And so inside this, this link function typically is nonlinear, so that introduces the nonlinearity in the model. However, the dependence on the parameters or the predictors as well is still linear, in the sense that essentially you will perform a linear combinations of the features using some beta star, and then this will be feed into this f, and then that gives you the y. And so typically it is assumed the y's and x, these data are independent, identically distributed, and then the y conditional x is following some exponential, some distribution from exponential families, such as Bernoulli. Then you have logistic regression, and then Poisson, and so on. So you can see the difference of this from the linear regression model is we have this f, right? And but otherwise it is very much like a linear model. And so the goal here is to, given these observations, to recover the underlying true parameter, which is called the beta star. And so the motivation, and so for example, logistic regression, like we said, is one of the simplest form of generalized linear model, and it is also used for binary classification, where the response is binary, and then in that case, this f is a sigmoid function. It maps the real line to be between 0 and 1. And the meaning of this is this tells you the probability of the y being 1 or 0. And for multi-class problem where the y is categorical, taking k possible values, and this link function is going to be specified by a softmax function. So it's something similar. And then for count data, and we can also use it to model the y is any negative integers, and for example, the Poisson problem. So I started to become interested in such problems, and since 2016, we had a paper on basically low rank matrix recovery problem, but with Poisson observations. And so the motivation there was that you observe entries that are counts of some underlying matrix, right? And so for each entry, you have a count. You want to keep that integer structure of your observation. So, and realize that, oh, actually, most of the matrix, low rank matrix completion and recovery problems are for additive Gaussian noise. But not much work are on the Poisson observation, for example, and not much are on the GLM, generalized linear model. And it turns out that you need new algorithms and a different analysis in order to do that. So that's where I think I started to become interested in this. And then over the years, I find out actually this is a very, very useful model for many real world problems. And that's where I start to, thinking about the so-called generalized linear model. So it's a mouthful. So what do you mean by generalized GLM? So it's a basically name we coined, and basically this is just a sequential version or time series version of the problem. And so here we have observations, which are xt's is the predictors features, and the y's are the responses, and we can possibly have the y's being a vector as well. And the xt's could be a matrix, and for example, where does this occur? It could be multidimensional time series, and so you observe the y's, which is m time series, and the xt's are the past observations, but you have m time series that you want to predict at the same time. And a lot of this coming from spatial temporal data as well. I'll give examples. And also in multitask learning, where this YT correspond to, you want to jointly predict multiple things at the same time. These tasks are related to each other. So, and those are the settings where you can generalize, like the response is a vector. And another thing interesting is we want to consider possibly these omega t's observations are not IID, but they have dependence across dimensions, and they can have dependence on the history. And so because of that, we consider this generalized version of GLM, basically still have the structure, and now consider I've defined the predictor as all the past information. So when I want to predict the observation at time t, I will use all the past information, including both the prediction and the responses, and also the current predictor. And then the relation is going to be through some f. Again, this f is a no link function. This part is the same as GLM, and this beta is the unknown parameter. And so this beta can be a matrix, and the meaning of this is, since you can see this is kappa, right? So kappa is the total number of parameters that you want to use, because the predictor we have is the past information, and depending on how much memory do you want to consider, and you will have a different number of parameters. We'll make these more specific. Okay, so again, the purpose is you want to, given all the observations with possibly spatial temporal dependence, and try to recover the beta star to design an algorithm for that. Okay, so why do I want to study this? And so I become interested in this initially because I want to do spatial temporal data modeling, and in particular crime data. So that was, I think, 2016. And so I live in Atlanta. And so one day the Atlanta Police Department come to me, said, we have a lot of data in our database. We have, over 10 million of cases. And we know the location, the time, the category of the incidents, and also the description in the text form about these cases. And we only have a small team of 10 people of crime analysts look at this data, these reports, and try to find the linkages between the cases. And he said, we heard you guys are doing some artificial intelligence things. Can you develop some algorithm to help us find the linkages automatically among these cases? So that's where it all started. And then,
Excuse me, we have a question in the chat. Do you mind if I interrupt?
yeah,
Okay.
sure,
This is
sure.
from the previous slide. So is beta random also, or is it assumed to be deterministic?
The beta is deterministic. Yeah, thank you.
Thank
Yeah,
you.
so yeah, this is not a Bayesian version. Great question. So today is a frequentist talk. So I know if they assume beta to be that could be another interesting problem. Yeah, beta is
Great.
determined.
Thank you.
Thank you. So yeah, thanks for monitoring that. Okay, so let's keep moving. Yeah, so and then I started to think about like how do we model crime data? And so it's a spatial temporal problem because the data are, you have a sequence of observation, each one is a crime incident. You have the location, the time, and also some marks. These marks are the description. Okay. And then in particular, we asked them, okay, what do you mean by linkage among these cases? And so they said, okay, this is the crime done by the same criminal or the group of criminals. And so in particular, they give me an example of 22 cases burglary by the same criminal. So clearly this person is very good. And he was caught only after breaking into 22 houses. And so they're hoping like if you can find the linkages earlier, and then put them together, you can identify who is a potential suspect and maybe call this person before he have broken into so many houses. And so, and then I realized, I learned that there's something that is a critical assumption to model such data, which is called a broken window effect. So this broken window effect says it's a phenomenon that's known in criminology since the 80s. And once a neighborhood has a crime happen, it makes a similar crime more likely to happen nearby location. Okay, so for example, for these 22 cases, we plot them on the map, and then you can see they're pretty clustered. They're all in certain part of neighborhoods in Atlanta, and this is actually our nice part of Atlanta. That's more affluent, I think, neighborhoods. And then it happens in a few months, so it's pretty clustered in time as well. And so actually, by looking at these locations, I realized that my home is here. So I'm surrounded by the incidences, all the things happened around me. And it gives me a lot of motivation to study more how to do this. And so, yeah, so basically here, like I said, the key assumption in modeling crime incidents is to consider this kind of spatial temporal dependence that things happened in the past may trigger similar things happen in the future in the nearby locations. Okay, so and turns out that such kind of spatial temporal data, right, spatial temporal dependence data is very common. So the data is in the form of the time of the incident, location of the incident, and also some additional marks. And so in a crime data example, the mark is the police report. And so there are, for example, social network data, the X data, right? So the mark are the tokens, right, of each of the tweets. And then it also happens in neurospike train and in earthquake catalog data, and those tells you the marks are the magnitude of the earthquake, when and where, and the magnitude of the earthquake. And this police report, and also COVID data, you can observe the number of incidents, the number of COVID cases, or now I think flu, each of the counties in the US, you can see the dynamic, and then power grids, I look at some of the power grid outage data as well. And so here, the problem is you want to take this data and then try to model this kind of triggering effect that something happened and it will make similar incident more likely to happen in the future. And so this essentially is a type of spatial temporal dynamic. And can we learn a model that can capture this dynamic from data and make predictions about the chance of something to happen in the future? Okay, so given this motivation, and I talk about generalized linear model, GLM, and then spatial temporal data, how are they related to each other? I will show that the spatial temporal data with spatial temporal dependence can be modeled as a time series version of generalized linear model. Okay, and so for example, let's consider a simple model, and I discretize the space into grades and also discretize time into grades too. Okay, so we'll discuss whether or not this is a good model, okay, and what setting this will be reasonable and so on. But for now, let's consider such a simple model. And so suppose I discretize my space to be fine enough, and then my time is time grids is fine enough. And then my observations, consider these crime incidences. They don't happen very often, right? So they don't have it every minute or something. And so then I look at each grade in my space and time, and then I will either have 0 incident or I will have 1 incident. So this encodes my observation. It tells me at any given time and the location whether or not there has been incident there. Okay, and so this T is index for time and the K is index for location. And so suppose now, essentially after discretizing this, and that I can treat this problem as observations. You can think about this as, a matrix, or if you consider location closeness, this can also be a tensor. Or if you want to consider some locations have more impact to each other, then you can have a graph problem. And so essentially you want to be able to recover the mechanism of this. Okay, here's more details about how we're going to capture this. So suppose now we take our data, which is in the form of omega tk, and then we basically say that let's take the past observation, and then we're talking about, these are only 0 1s, and so that means I can model this as a Bernoulli observation. And then this probability of getting 1 incident, I can use the generalized linear model kind of model. And so I have this beta k, right, that captures the intrinsic probability of having event here in this location. And then the second term basically captures things happened, some periods ago. This S is my lag. And then, it could be happened at the same location, but it could also be a different location. So this beta KL is capturing things happened at a different location as periods away. How does this impact my, current time and current location? Is captured through this beta KLS. And so this is the model, for example, to capture the spatial temporal dependence of the past incident on the chance of having incident at this moment. Okay, so and then we realize, okay, so this model essentially, if I redefine everything, and so I define some eta, and this eta contains all the observations. So what is this omega? This omega is my observations in the past at all the locations. And so you can see here, I assume something called a D. This D is the memory depth. So for example, I only want to consider things happened in the past month. Maybe things happened months away or too far away. I don't want to consider. So you can control this D. And so, and that's my, all the observations between time t minus d to t minus 1. And then I use some, simple linear algebra. I can write this whole summation into the form of something, right, contains my data and multiply the vector. Okay, what is this vector? This vector is basically contains all the parameters you want to consider. That captures the intrinsic probability at each location, and also the interactions between locations as periods away. Okay, so it could be a long vector, right? So this is a model. I would say it has some parameters, but it doesn't assume a lot of structures. So this is very flexible model, but you have to estimate a lot of the parameters at the same time. And okay, so this basically is one motivation, like why I want to consider generalized linear model. Yeah, right. So I take my events data, convert them into binary, and then I have to use a Bernoulli model. And so this spatial temporal interactions are going to be captured through these coefficients. And so it turns out there's another motivation, which is, I think, quite important for modern world, which is language modeling. So this is actually another aspect of data. Like I mentioned, these police reports have the text component. So it's basically when you investigate these incidences, the police will enter a description of the incident. Right, so each incident are having a lot of information in this part. So when we model these incidents, usually we don't just we can't we don't want to just model the time and the location, but also a detailed description about these incidences. And in particular, in that Buckhead burglary example. And so, the police told us that if you look at the description of these incidences, that's where the most important informations are. And then that, for example, is that there's a pattern in this bad guy doing these burglaries. So if you're look at the incidences reports, you will realize that this guy have he always dig a hole in the back door and enter the bedroom, ransack the house, and find jewelries and valuables. And so those words actually appears pretty often, and so on. And so basically, the idea is we want to be able to jointly model these incidences, consider their time, location, and also the text description parts. And so if you want to model the text, right, so this is, police report is a particular kind of text, but in general, right, all the texts is a sequence of words and phrases, and they have dependencies, right? So in order to model the, text, we have to consider dependent data as well. So it's a kind of Markov model. Okay, so yeah, so we did some investigations of, how to use this kind of model to perform time series modeling, and in particular, recently we had a paper on using this technique to perform nonlinear time series embedding, and it does pretty well, and we can achieve really good performance without using neural network even. There's another paper related to this one. Okay, but the motivation is, again, you can use this to model text. In that context, and then it's also a prediction problem. You want to predict the words and phrases in a certain position in the text, and it will become some kind of categorical distribution, right, modeled using a softmaxing function. Okay, so tying it back, so our story is we want to take our data and then try to estimate, a model. The model is basically encapsulated by some parameter beta. We'll talk about actually this beta will have some structure as well, as you can imagine, that we can possibly utilize. And for example, right, so this beta can have location, it captures location, and so maybe locations that are close to each other are going to have more dependence that are far away from each other, less dependence, or maybe there's some graph structure. So let's say all of this constraints or prior knowledge, you can actually contain in this, feasible sets or constraints on the beta. You would say, I want to consider the beta with certain structure. It could be sparse, could be a low rank, but if I, put my beta into certain matrix or tensor form, it could be low rank, or it can be a, graph structure. And so I just encapsulate everything into this feasible set X. And so, and then I want to fit my model by choosing certain loss function. And so in the GLM model, usually you would say, okay, let's consider all the observations RID, and let's just consider this. Okay, so you average this loss across all the samples and try to solve the, for example, maximum likelihood. You want to maximize where the L is the likelihood function, and then find the beta within your feasible set. And okay, so the rest of it, we're going to talk about whether or not this is a good way to estimate the beta. And in particular, remember this beta can be pretty high dimensional, right? We have lots of parameters. And then is this a good approach? And then what is a good choice of the L and how to make it better? And with algorithm guarantees and also hopefully statistical guarantees. Okay, the usual story of the generalized linear model, okay, is if you choose, for example, maximum likelihood, where this L is a log likelihood function, and then because of the property of exponential family, this loss function is going to be convex. And then if I choose my feasible set, is also convex. And for example, I assume this beta are, this X is all the L2 norm of beta less than something, or it is L1 norm is less than something, and it is convex. And then this whole problem is convex. Okay. And then convex problem is great. That means I can use many algorithms such as first order methods, gradient descent. Then I will converge. And then statistically can also show that because the property of the exponential family, then you can recover the true parameters. So life is good, and everything is good. And however, in practice, it is well known actually when the sample size n, is not very large compared to the dimension of the beta. So remember, we're in the in a world where beta can be pretty high dimensional, and n can be large, but beta is also very high dimensional. So the convergence can be a little slow actually for solving MLEs of the GLM because the landscape is pretty flat near the true parameter. I'll give some examples. Okay, so here's one example of a bizarre kind of logistic regression problem. Remember here, the y is it's binary, and then it's modeled as a Bernoulli, and then my link function, usually is chosen as a sigmoid. Okay, so now let's just consider, it doesn't need to be sigmoid. It could be other link function. Okay, still give me the mapping between 0 and 1, so it's a legit link function, and I will consider a arctangent link function. And so this is, the sigmoid is this red one. And then this blue one is the arctangent function. You can see it is just, transition is a little faster than sigmoid, but it is also a valid link function. And then let's look at this very simple simulation. And you can see what happens here is I have, this is my true model, the probability y equals to 1. And given one predictor, which is x, is f, right? This activation function, right? And then, which is, arctangent activation function, the true parameter is 3 and minus 0.1. And my sample size is 500, which is, supposedly not too small for such a small, simple problem. And then I solve for the maximum likelihood of the problem, okay, to try to recover my true parameter. So beta star is my true parameter, which is 3 and minus 0.1, and then I use gradient descent, step size is 0.1. And so this red one is basically the difference between my estimate after, this many iterations from my true parameter. So what you can see is, first of all, this GD, although it takes some time, it seems to converge, but it's actually converged to something off. And that is because in theory, when the sample size is infinity, it's large enough that you're going to converge to the true parameter. But however, here you actually are a little off, and it converges, eventually to something a little off. And so, but what is this blue line? Okay, this blue line is using this proposed technique, which is called the variational inequality. Okay, VI, that I will introduce later. That this is why we need to introduce this new estimation technique. You can see it actually converges very fast, right? Pretty fast, and actually converge to much better solution, right, of the true parameter than the gradient descent of MLE. Okay, so hopefully this is one example illustrating why do we need that. Okay, so the first example is to say that, okay, suppose I consider a simple logistic regression. I just change my f a little bit to arctangent function, and why I make this tweak, I'll explain as well. Just keep that in mind that I tweaked it a little bit. But I created this situation that gradient descent of a convex function actually converges to a solution that is, converge slowly and also not a super good solution. Okay, now let's consider a different formulation, which is suppose now I just want to say, okay, instead of solving maximum likelihood, can we try a different loss function? Okay, so a lot of people are also using least square as a way to fit the model. Okay, so it's still a reasonable loss because my y is, although it is binary 0 or 1, but you could say f output is close to 1 when it's that indicating that the y is more likely to be 1. So in many places, the fitting of the regression actually you can also use least square. Okay, and however, if you look at this, and this time this whole problem is not going to be convex anymore, and so the non-convex is mainly because this f is non-linear, right? So when f is sigmoid, when that's arctangent, whatever you choose it to be, the problem is in general non-convex. And for non-convex problem, we know it can be a bad story, right? And so here's one example constructed by Arkady Nemirovsky in one of his talks. And so basically what happens here is he generates some examples, which are yt equals to arctangent. This is the predictor and added some noise. And then basically what's shown here is you can see the green one is the true parameter. Okay, it's here. And then basically, if you look at the least square loss, and then that's going to be corresponded to this blue one. Okay, so you can see, okay, here's a range, which here restrict to be from -20 to 20. And then you can see if, you have a local solution like this one. This local solution is not too bad, but there's another solution, which is here, right? It's completely off from the green one. So depending on how you initialize, if you're lucky, you can get not a very bad local solution. But if we're here, we will be getting a completely off estimate. And this is, expected kind of because of the non-convex nature of the problem. You cannot hope to get, to localize it or you recover the model because of non-convex nature. Okay, so hopefully that gives the motivation why I want to consider GLM, and then why estimation problem needs to be solved, right? So can we find an algorithm that actually hopefully can recover the true model, the parameter, and then also be able to, be computationally efficient and have some guarantees. Okay, so the new story is instead of estimating generalized linear model or GLM, which is just a twist of that, this temporal dependence and the multiple dimension responses. And we use something not by maximum likelihood, not by least square, but using something called monotone operator variational inequality, monotone VI. And so in a nutshell, I think the slogan is this is going to turn non-convex problem into convex problem. So how is it possible? And so it's basically like a first order method, but without using gradient of a loss function. But it is going in a direction that is by construction going to give you the correct parameter. Okay. So what is the intuition behind? And so recall if you consider generalized linear model, and so that basically says the response condition on the predictor is going to be F, and then right, so beta star. And so you can see that I consider some G, okay? And this G is defined as I consider the average over X, right? And actually you can do X over and the Y as well. So taking expectation, and then inside here I have F X transpose beta minus Y, and outside I multiply X. And so you will see if I define my G this way, and then if I plug in the beta star, which is the true parameter, and then G beta star is going to be 0 by construction, right? Because in expectation, this should be X and Y. In expectation that this is going to be the same as this, right? So on average, it's going to, beta star is 0 of the G beta. So true parameter is the root of the G beta. And so basically, this says that in order to find the true parameter, the problem is to find the root of the G beta function this way. And if you look closer, what does this G look like? This G function, it basically is in the form of, you look at the current prediction using some beta, and then look at how is it different from my response Y. And then look at this residual, and then from the outside, you multiply by the conjugates of your design matrix, right, or your predictor. Okay, somehow it has this form, but it has a connection, I think, with a lot of the algorithms that we're familiar with, such as the ISTA and FISTA type of algorithm for solving, least square problem type of problems. I think it has some motivation from there. Okay, so this is in population. And in practice, we can design an algorithm which is by replacing the expectation by sample average or SAA version, and then you can construct this G beta. So what is the algorithm? So the algorithm is, let's take our data and then let's form the G this way. And now let's just use G as a gradient, okay? And so the G is actually not a gradient, not necessarily gradient of anything. It doesn't need to be. It's just by construction such that the true parameter is a fixed point, is a root of G. And so you just take the G, and then you run an iteration as if G is a gradient. You run this kind of iteration. So it's almost like a projected gradient descent, except for that this G is not necessarily gradient. It's just by construction, our monotone VI. And so here, the usual thing, right? So you project on the feasible domain, and inside here you have the step sizes. And so you can do it this way, or you can also use it to, with any of the accelerated versions, such as momentum methods and so on, and treat this as a gradient. Okay, so this algorithm actually works. And let me show you actually how it works. And this blue line is what we get. For this example, using G instead of the gradient of the likelihood function. And this, you can see they got really fast conversions and actually converge to the right place. Okay, so why this works? Okay, so this basically behind the scene is that use this G to run this iteration correspond to solve the so-called monotone operator variational inequality problem, which is basically this. Says find the beta within your domain, within your feasible domain, such that you satisfy this. Okay. And so, yeah, this is the beta here. So if you look a little closer, what does this mean? And this actually is reminiscence of the first order optimality condition for solving convex optimization problem. Okay, so but like I said, I think the interesting thing is this G hat in the GLM setting is by construction. It is not necessarily a gradient of any loss function. And so according to my colleagues, is that the solving VI with monotone VI is the most general problem with convex structure. It is a convex problem to solve a feasibility problem like this. And I think I saw a question. Is that right? How to initialize, define the feasible domain? Oh yeah, so here I just treat you can initialize, right? So you can make a guess. For example, I guess for our problem it's not too difficult, right? So the constraints are, for example, just start, with a beta with, bounded norm, or if you want the beta to be a matrix with low rank, you can take some random low rank matrix to a, SVD and truncate to be low rank or things like that. Yeah, so that hasn't, I just suppose I have some initialization within my feasible domain. It's not too difficult here. Okay, so thank you. And one more question. Yeah, good. And so, okay, like I said, what is this? What exactly is this thing, this monotone VI problem? And if you actually compare it with another thing, which is if you solve the problem minimizing a loss function, this L is convex. And then from convex analysis, we know that the optimal solution is the beta that satisfies this. Okay, so if your L is convex, you solve the problem minimizing convex function, and then the optimal solution should satisfy the gradient evaluated at the beta and times inner product with u minus beta for any u in the domain should be negative. So pictorially, this is what happens, right? So you have some contour of your loss function, and then this G is the the norm vector, right? That's orthogonal to tangent, and then so you look at this particular point that everything in your physical domain is lying to one direction of that. Basically, that's what happens. But actually, oh, okay, this is the tangent space. But actually, the problem of VI is directly casting this as saying, let's find this beta. If I define the G this way, let's find a beta that actually satisfies this. And again, the G doesn't need to be any gradient of any loss. Okay, so now let's look into like this mysterious thing and from a particular example. So let's again consider this nonlinear regression problem we said earlier, which is non-convex, so it has the trouble. And so this is our loss function, right? So you take the gradient, and then by chain rule, you will have something like f prime and times everything inside here, okay? And so now recall, what is my definition of the monotone vector field? And so you can see one thing, which is interesting. The only difference between the gradient of this non-convex loss and versus if I used monotone VI is that I don't have this red term, which come out of the chain rule, which is the derivative of my f, okay, evaluated at this. And so, okay, this basically says, all right, if I use this, the gradient of this, and it is that because that is gradient according to for a non-convex function. However, if I just modify this a little bit by dropping this red term, and then all of a sudden I am equivalent to solving some convex problem. Okay, so this modification is the key here. And so here's another example. Okay, so this example just say that I suppose I have a loss coming out of this non-convex regression problem, right? And here's another example, which is let's consider, okay, logistic regression, right? So now the problem, the objective function is maximum likelihood, where you minimize the negative log likelihood function. So let's see what's going to happen here. And now this is my loss function, okay? And now let me take the gradient with respect to the beta. Okay, so by chain rule, after some rearrangement, you will find out the gradient looks like this. So I have this green term, this blue term, okay? So again, if you compare this with VI, and this blue term is something additional. So what is this blue term? It's f prime. My link function takes derivative divided by f times 1 minus f. Okay. And so you ask, is this always going to be different from the G? So from the previous one, usually this term is not constant. So clearly the gradient is going to be different from monotone VI. However, in the logistic regression, there's interesting observation, which is if you consider the link function being the sigmoid, and the sigmoid function is very special, and the derivative of the sigmoid is equal to f times 1 minus f. Okay, so if I plug that in here, you realize, oh, for the logistic regression with the sigmoid function, actually this cancels with this. So for logistic regression with sigmoid link function, and the gradient is going to be the same as monotone VI. Okay, so actually for this very case, they're the same. And then, however, if I consider a different link function, that is the arctangent link function that I talked about before, and again recall that arctangent is different from the sigmoid because it also maps between 0 and 1, but it just has a slightly sharper transition. And then you do the calculation, you realize this f prime divided by 1 minus it actually looks like this. Okay, so it is not going to be constant. And then the gradient and the monotone VI are not going to be the same. And in fact, numerically, you can see this difference. Numerically, you will see that you have this gain. It performs better. Okay. And it doesn't have this issue of slow convergence and possibly conversion to a not very desired case. Okay, so it's quite theory is that using this G hat, which is not necessarily going to be anything, that actually give us better algorithm to estimate the parameter, the model. And can we say something theoretically, right? In terms of both algorithm convergence guarantee and statistical guarantee, this actually gives the true model. And so this is summary of what we have said so far. And now let's dive into the theory and see why this works. And so, okay, the whole thing actually is built on top of this theory of monotone vector field. And I don't mean to dive into everything because, but this is basically the background information. So what is a monotone vector field? So everything that satisfies this definition is monotone VI. And so, and then if this inner product of the GZ and GZ prime and inner product with the difference of the arguments is some negative, is called a monotone vector field. And if it's further greater than some constant, positive constant, non-negative constant times z minus z prime is actually, modulus is called a monotone with modulus kappa. If this kappa is strictly greater than 0, that's usually what we need in our cases that actually give you the convergence rate. And so, yeah, so basically you can verify the G we defined earlier for GLM will satisfy this. And so in fact, the special case, what does this become? So if you just consider a function, right, that m equals to 1 means that your y is just scalar. And so this just means that if you look at the derivative of the function, the derivative is always greater than or equal to 0. So it's monotonic increasing. Okay, so for example, sigmoid function satisfies this. Okay, so it is essentially what happens here, this construction is a monotone vector field, because you take your sigmoid function, which is the monotone function in 1D, and then you do some vector matrix expansion of this function using this rule, and essentially you use the same sigmoid function or same monotone activation function for each of the components, and then you can also do the composition of A transpose inside and A outside, and that will preserve the monotone property of your function. And that's, you can see where the construction comes from. So you can actually show this holds for our problem. Okay, so where does this come from? Okay, so again, like I said, if you use the G hat we constructed earlier to do gradient descent, that's equivalent to solve the so-called monotone, variational inequality. And this is a very actually classical topic. It's a powerful tool for finding equilibrium. And our problem, essentially, equilibrium is the true parameter by construction. And it has been used in game theory, OR, engineering. And so it's actually very popular in modeling traffic equilibriums. So I think that was the work by, for example, Dafermos, Naguni in 2022. So for civil engineering people, I think this is something they're familiar with. And the use in OR and in particular statistical estimation is a little more recent. And so, for example, Anatoly Juditsky and Kadin Nemrovsky, I think they're the first people to consider this, using this technique for estimating GLM. And then there's also this recent book actually uses to solve large-scale convex optimization problems. So it actually converges, computational-wise, pretty efficient. Okay, so now finally, right, so what can we prove? And so basically you can prove if you use this G, right, as, to replace your gradient in solving such problems. And you can first show, this kind of results that there's this algorithm convergence, right? So this beta is a true parameter. I think you should have a star. And so after k iterations, and then you will converge, you have this kind of convergence that shrink with k, right? This kappa actually is the modulus that we defined earlier of the monotone vector field. And if you have a diminishing step size, then you can have this. And this expectation is respect to the randomness in data. Okay, so we can also develop the, improbability version of such results, but this illustrates the nature. And so this was from the early results. And, the more recent result is we can remove the expectation. And so here are the summary of the basic structural assumptions. All you need is you have a convex domain, and then the G or the gradient, the direction we're going is basically a monotone VI the construction and some other regularity conditions. And okay, so I think this might actually give a little bit of highlight, like how this is proved and where this is used. And so recall we have this kind of iteration. And so basically the analysis is very much similar to the basic gradient descent analysis. So if I plug in the beta k in regarding to the previous point, you have this, right? And then it's going to be upper bounded by this. And now from here is I just do quadratic extension to break into 3 terms, and you're going to have this term, this inner product, right? And then you realize, oh, why do I need this G to be a VI? Is because, I want this term to be non-negative, okay? So this is basically where the G actually comes from. So you can see actually in solving convex optimization problem, the gradient of the convex loss function will satisfy this is greater than or equal to 0 because of convexity. And here, basically, this is taking a different route. Again, saying without assuming a loss that induces the gradient satisfy this, let's just directly construct the G satisfies this. And actually, that gives you the convergence. Okay. And so the rest of it is very similar to, I think, the familiar gradient descent analysis. And then if you consider some closeness to the true solution, let's call it dk, you can prove that in each iteration you can shrink the decrement, okay, closer to the true solution by this amount, right? This is going to be this, the rate of the convergence, comes from, it's 1 minus 2. This kappa is the modulus, and the step size, you can see that's why we choose the step size to be diminishing. And then yeah, so this is just basically where this convergence result comes from. And so this is the other result, which is a statistical guarantee. And so basically, why can this give the correct solution? And so like I said, the intuition is because the true parameter is the fixed point of that G by construction. And so in fact, we can show that under this previous structural assumptions, using the G hat and random iterations, and we can guarantee this. So we can get close to the true parameter, and the error bounds is given by this. And so you can see this is the general type of bounds with R. Here's the R norm. And so we can make this more specific, which is this norm is going to be bounded by something here. Okay, this is where I think you also see like why, this is where we can also explain why this actually converges better even than MLE you can converge faster. Is because you can see this actually depends on something almost like the smallest eigenvalue. And then inside here, let's see what are these things. So the n is a sample size, and okay, so I think what I called P was actually the dimension of the parameter. So the dependence on the problem dimension is log, right? Since epsilon is here, so it's a high probability type of results. And so this is good. This means that dependence on the dimension is log. So, and then you have the usual type of rate, which is 1 over square root of n. And then this part is interesting because this basically is depending on the property of my design matrix. So this X, remember, is my my observation, my predictor. So this basically says that how good I can to get close to my true parameter depending on these modulus. What are these modulus? For example, we can bound theta2, and the theta2, this dependence is 1 over the square root of this, these two thetas, right? So, but you can see if the theta, if the theta is smaller, that means this error error bound is bigger. And so my lower bound, I need the lower bound. The lower bound for theta2, theta2 means that if this R is 2 and when R is 2, this is like the L2 norm difference, right? So theta2 can be related to the modulus times the smallest eigenvalue of my matrix. Okay, so what I have here is basically like, instance dependent bounds that if I have my predictor, I can actually show that, how good or how hard or how easy it might be that we can recover the true parameter. Okay, so to mention that in the proof, actually, we also need to handle the dependence across the beta, across these xt, right? Remember, there can be spatial temporal dependence. In particular, temporal dependence can be handled by, a not too difficult Martin-Gall argument that we can get this. And okay, I guess that's, how does this perform? And I mentioned the Atlanta police data example, and this is one result we can have from this kind of, and so we fit these parameters, right? So the parameter tells us how the past incident at one location will impact the future incident. And so here we tried two types of crimes. One is a burglary, the other one is robbery. And so you can see this model can capture the influence of the past incidents, similar incidents to the future incidents of the same category, but also the incidents impact across different categories. And so this as indicate the lag. This means the incident happens 1 period ago, 3 periods, and 6 periods ago. And you can see what, we discretize the location, and this is downtown Atlanta, I guess near Georgia Tech. So there's a lot of burglaries and robberies. And then you can see that we discretize location to be 4x4, so there are 16 grids. And so here, this basically, the black line is proportional to the intensity of the beta estimated from the model. The darker it is, the stronger the beta is. And so you can see actually interestingly that over this different lags, there's some kind of dynamics happening, like indeed the nearby location will tend to have an impact on the other locations, right? So this is basically how to interpret this result. And okay, this is a recap of how the model is set up, right? And in particular, the G, right, in this case is constructed this way. And then once we have this model, right, because remember our observation is either incident or not incident, we have two types of incidences. And so is this a good model? Is it reasonable? We also compared the prediction. Prediction is talking about the probability of having incident at each of the locations in the next time period. We compare the predicted probability with the observed probability or observed frequency of the incidences. I think the numbers, of course, it's very difficult to get something completely right or accurate, but I think the numbers make sense. For example, this is the true frequency, which is 0.14 at location 1, and the predicted probability is 0.17. And you can see this one, right? This location 2 is significantly more safe. So and this is reflected that you have a 1 significant digit smaller chance of getting a burglary. And sometimes introducing constraints, these constraints are in the shape of my beta. For example, I want my beta to decay over time, and then you can have better predictions. I guess I'm running out of time. Yeah, so here just also verifying what does this theta looks like, that impact from these appears in my upper bounds. I can evaluate using my data. And because in real data, I don't know what my ground truth is, but using this actually can help us to have a feeling how close we are from the true, possibly true model. And so some of them are larger than others. Indeed, they have better performance. Okay, so I guess I just want to mention we also use this for, like I mentioned earlier, sequence models, language modeling, and this is our latest paper in the machine learning conference. And so we'll use it for example, to find embeddings. Okay, so the model here is going to be this kind of softmax models. And so once we have the parameters, we can use the parameters of our language sequences to find out embeddings of the documents. We did this for some applications such as authorship detection in the embedding space for the text document. So this is, you can tell Alice Adventure in Wonderland, and through the Looking Glass, these two are written by the same author because they are being put in the same cluster, and all the archive abstracts are in the different clusters. And so this is basically looking at different cluster strains of influenza because it's also a sequence model. And the last one is the genome sequence. All of these are sequential models. We also, tried this to show this can be used for training neural networks to get faster convergence because neural network can be viewed as layers of, GLMs. And then finally, we also try to say to look into, okay, so you discretize the time. Is it a reasonable model? So motivated by this, we consider an arbitrary time grade, which we call time uncertainty. Turns out that leads into a new type of link function. And then we use this technique, and this shows again good performance, better performance than using gradient descent. And this can be used to discover the dynamics of the disease progression for sepsis prediction. Yeah, I guess that's all I want to talk about. In general, the story is about there's this new way of performing statistical estimation for generalized linear model. And basically, the story is that this can cast the problem into a convex, equivalent. And because of that, we can have convergence, algorithm convergence, and also statistical guarantee. And empirically, seems to work pretty well. And so we're working on incorporating the structures and already have some results like if the beta, the beta parameters will have some structure, a sparsity, low rank, and graph, for example. And then this can help us to, you can introduce regularizers, you can design your X, your feasible domain with such structures, and that actually can be better. Okay, I guess that's all I want to talk about. And I want to thank everybody for attending, and thanks organizer. I want to pull out this one in case you have, you want to know where the papers are. Thanks, everyone.
Thank you for the great talk. I guess we can take a few questions if time permits. If there's questions from the audience. Okay, maybe I can have a naive question.
Yeah.
So I saw the variation inequalities and the textbook is shared. Actually, when I was learning this, what
Oh.
the instructor, what and Ernest.
I see.
Yeah. So when you so it's this kind of the G hat is by construction for
Yes.
has to be by construction for specific F with kind of nonlinear activation functions.
Yeah, so basically this G, the construction this way is pretty general. Okay, this particular G works really well for, excuse me, GLM and GGLMs, which are basically the same thing, right? Slightly variation. So, and so I think in the general